So we're nearly done. Example 5 says if the population of the United States continues to grow as it has since 1980, then the approximate population in millions for the United States in the year T, where T equals 0 corresponds to 1980. That's a good year. 1980 was a really good year. Will be given by the function this. Okay, this gives you the population of the United States after T years after 1980. So estimate the population in 2020. So what would T be? T equals 0 is the good year. So 40. When T is in 2020, T is 40. So all you're finding is P of 40. So you're going to do 227 e to the 0.0093 times 40 power. So to type that in, the biggest thing with this is I just want to make sure you knew how to type these in. So you're going to do 227, and since I'm going to raise e to a power, I'm going to use this e. 0.0093 times 40, enter. So 329, is that in millions? Let's see, yeah. So that many million. 329.29 million. Yeah, in the United States. In the year 2020. When will the population reach 750 million, which is over double what they're expecting it to be in 2020? Probably 2030, I don't know. Let's see if it's going to like double in 10 years, I don't know. 750 million, so all you got to do is take your function, set it equal to, because that tells you the population. Population equals this. So we're going to do 750, because it's in million, equals 227 e to the 0.0093t. And it's the same thing as a while ago. Move the 227 over since it's being multiplied. So we're going to do 750 divided by 227. You don't even have to do that step, it just makes it a little bit cleaner. Let's try that again. 750 divided by 227. I was seeing if y'all was watching. So you've got e to this power minus that, so let's go to y equals. Clear. E to the 0.0093, and since you don't have t in this, you'll have to use x for years, minus 3.30396. 3.30396. Hang it. No. If you use a letter T, it'll confuse the calculator, because it's this y is understood to be y of x. That x is going to be the variable you're going to put in there. And luckily, our scale from a while ago is going to work. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 20, about 130. Probably. Okay, remember that number, see if you're right. 0, let's say between 120 and 140. 128.5 is way off. So T is, well, we can write it right here. 128.5. But if you want to actually write that in years, 0 is 1980. So T equals 128.5 will be add 128, 1980 plus that. 1980 plus 128.5. That's going to be the year 2108. And 6 months into it. Good job. Yes. Here you go. Other exponential functions. This is the last part of the section. Here's the thing about it. When we're talking about population growth, this hopefully will make you feel a little bit better. There's a cap on it, because it says normal exponential functions continue growing without bound, like in the problems we just saw. It just keeps growing, but eventually it can't grow anymore. In a logistic model, limited future growth is taken into perspective. This could be due to fixed area, food supply, or other factors. So the positive here is before the population reaches so much, we'll run out of food and people will die off. So that's the positive of this. Hopefully not. So think about this. The population of a certain the population of fish in a certain lake at a time t months is given by this function, to where it is an exponential function because you got e to the, and you got a variable in exponents. There is an upper limit on the fish population due to oxygen supply, available food, etc. Same way with us. You'd get to a certain point to where there couldn't be any more people. And think about it, in a pond, if you've got a pond, eventually, it's going to look funny if there's 1 million fish in there and they're all packed on top of each other. There's a certain point to where you get to where you're not going to have any more fish. I don't know. So here we go. It says graph the function on the graphing calculator, step 1. So let's do that first. Second, let me clear my memory because I've got a ton of stuff in here. So y equals 20,000 divided by, and put the bottom in parentheses so you'll divide by all of it, 1 plus 24 e raised to the negative x over 4, where again x would be the number of months in this case. And look what this function does. Well, if you could actually see that it's going to go up and it's going to level off, if I can think about. So let's see, I'm going to have to change my window big time, and you'll see hopefully after this problem. Well, first off, x is your months, so we can start 0. Let's do 0 up to 36 months, which would be the first 3 years, where my scale would be 4. And, well, let's do 6 to where it's every half year. My y, I'm going to run from 0 up to 21,000, to where 1,000's my, and like I said, hopefully after this you'll see why I did this. Here's your exponential model here. Notice it looks like your normal exponential equation, but once it hits a certain point, levels off. By looking here, can anybody guess what you think that leveling off is going to be? Where do you think it's going to? That's fine if you don't. So there's the graph of the function. We just did that. What is the number of fish after 5, 20, and 50 months? So you can plug in 5, 20, and 50, but let me give you a shortcut here, guys. Since you graphed it, there's no need to do that. After 5 months, why not just do trace? After 5 months, hit enter. There's 2,539 fish. After 10 months, hit enter. There's 6,733 fish. Do you make sense what I'm doing there? Do what? Well, it might be a huge pond though. After 50 months, it's not on my calculator. Be careful when you use the trace function. If it's not on your graphing calculator, it's going to give you an error. So let's do quit and let's change our window. So let's do 0 to 54. Where that's, I will. So you've got trace, 50 months, enter. Look what you got. After 50 months, there are 19,998 fish. Do you see that's where it's starting to level off? Let me clear that off. So it comes up and it starts leveling off, and after 50 months you're at 19,998 fish. Do you see it's nearly leveled off. Also, this goes back to the lessons we've done before. You've actually got a horizontal asymptote there. It's going to level off, but it's never going to cross that asymptote. What is the upper limit of the graph? 20,000. You're never going to have above 20,000 fish. Okay? And later on, I believe we come back and we revisit this problem, we talk about why. So any questions?